there have been photometric and spectroscopic survey in the past, which also delivered large volume of highly dimensional data, and specifically spectra is the very definition of high dimensional data in astronomy. Just to mention some of the survey which have been somehow involved, so Apogee, FANSTARS, and so on. And the future is going in the same direction. So in the future, we will have spectroscopic survey like Foremost or Sloan Digital Sky Survey 5, which will also deliver multiple spectra for billion objects. But in this talk, I will focus specifically on two photometric survey. The first one is the Transiting Exoplanet Satellite Survey, TESS, which just entered the second year of its extended mission, and it's delivering something like 27 gigabytes of data per day. And the other one is the Legacy Survey of Space and Time that Michele mentioned before, so LSST, which is going to start next year from the Vera C Rubin Observatory in Cerro Pachón in Chile. It will run for 10 years and deliver 20 terabytes of data per night. So again, it's really, I think it's self-evident that we cannot try to use our standard analysis tool. What I mean by that, just human interaction-based analysis tool to face this data. We need to use at least some degree of automated software that will filter out all the information that is not really relevant for our science case. And that's exactly what machine learning is great at. Right. So during this talk, I will focus on two specific projects. The first one is how we can detect exoplanets in the photometric data from the TESS, from TESS, and the other one will be about how we can detect slow-moving solar system bodies in LSST images. For each of these science problems, I will give a little bit of background and then describe what are the main challenges and why we need to use machine learning-based algorithms. Specifically, we use deep learning. It might feel like this is two different talks squeezed together, but I promise that it makes sense, because actually from the perspective of computer science, this is kind of the same problem, because in one case we are going to use one-dimensional convolutional neural network to do supervised classification, and the other case we are using a very similar model, so still a convolutional neural network, but a three-dimensional one, in order to do again classification. So these are indeed two projects from two master thesis projects in machine learning of two students, Stefano Fiscale on the top and Antonio Manzanello on the bottom, who I am co-supervising, who should discuss their thesis this summer. Okay, so let's start with the first topic, which is how we can detect exoplanets in TESS data. Well, in general, finding exoplanet is a hard problem, right? So we only succeed in doing that 30 years ago, so it's a relatively new field. And to explain why it's so difficult, there is the old but cold example trying to detect a firefly that is just in front of a stadium light. So basically, we want to find something that is small and faint, sitting just besides a stellar, luminous big star. But we recently hit the milestone of 5,000 exoplanets known to date. I think now we overcome also the 5,200 something. So this means that in these 30 years, we actually learned how to find them. I give a very brief overview of what are the most relevant techniques for finding exoplanets, just to, I don't mean to be complete on this, but just to give a briefing of how to do that. So the first one is by measuring, sorry. No. Okay, I was supposed to run a video, but doesn't matter. So the first method is by measuring radial velocity shift of a star produced by the gravitational pulling of the planetary system that is surrounding the star. The second method is the transit technique, of course, in which we are measuring the decreasing incoming flux from the star. Produced by a planet that is crossing the stellar disk. Then we have astrometry, in which basically we measure, as in the first case, the motion of the star produced by the common rotation of the system around the center of mass. But in this case, the motion is projected on the sky. And if we can block the light from the central star with a coronagraph, then we can also directly image the planets, but this only works if the planets are massive enough and at large separation. And finally, we can also use microlensing if the background star is lensed by a star surrounded by a planet. All these techniques are relevant because they allow us to probe different regions in the parameter space of the exoplanet population. In some cases, they are also complementary. Like sometimes it's useful to have detection with both methodology, the Doppler shift, and the transit techniques in order to get the bulk density of the planet. But if we look at the number of detection for each of these methodologies, you can see that the transit technique is the most prolific. It's thanks to transit, we found 77% of the non-exoplanet population to date. And that's particularly true if we look at this plot in which you can see the discovery for each of the methodology for a given year. This is specifically true starting from 2010 here. And that's because Kepler started to work, was launched and started to operate. So Kepler is a spaceborne NASA mission that was looking at over 500,000 stars for this is a little bit complicated, sorry for that. Like if you, yeah, so this video shows the number of planets discovered per year in the sky. And then you see that starting from, I don't know why it doesn't work, let's try this. Okay. And then at some points you will see in 2010, Kepler will start to kick in, and then you will have this part of the sky be intensely populated by detection from the Kepler Space Telescope. And it's actually Kepler alone is responsible for more than half of the known planets today. So building on the success of the Kepler mission, NASA also sent another space telescope to search for exoplanets. This is TESS, Transiting Exoplanet Survey Satellite. The strategy for TESS was slightly different. So the field of view of TESS is very big, is 24 degrees times 96 degrees. So TESS will point to a given position, then observe that sector of the sky for 27 days, and then move to the next one. Basically, in 2 years, the 2 years of the nominal mission, TESS surveyed 76% of the entire sky. So when compared to Kepler, the volume searched by TESS is more homogeneous, but it's less deep because the limiting magnitude of TESS is around 15. So it's, as I said, it's a slightly different strategy. So all the data collected by TESS, it's public. So let's say that you want to use this data to search for exoplanets. What should you do? So this is the conceptual pipeline. You can access the photometry, so you can download either the full frame images and do your own photometry, or you can also download directly the aperture photometry extracted by the images. Then you can do some pre-processing of the data, cleaning, training, binding, everything that is relevant to the specific light curve. And then you have to search the light curve for a transit-like feature, which basically means some kind of eclipse in the light curves. And if you do that, if you can also use the Spock pipeline for TESS that will allow you to find what is called a threshold cross event. So you at least need 2 events for identify a TCA, because you need to find the period of the eclipses, of course. And then once you identify this TCA, that's the more difficult part. You have to vet this signal to confirm if it's because of a planet candidate or something else. The vetting of the planet of the planet candidate is usually done by human interaction, by using either simply test data or supplementary observation when they are available. And you can do that like by hand, let's say, or using some statistical tools. But I will explain this a little bit better now by using a specific example. And then the last step is the validation of the planet candidate, which is usually considered completed when you have a paper that produce all the information needed to perform the vetting of the planet. So this is something outside, let's say this part is actually outside the test data, the part that involves the direct use of this data. Okay, so as I mentioned before, just to give you a better sense of how all of this work, there is a specific example of one system that we recently vetted. The paper is under review now. So this is a system called TOI 411, which includes a super Earth and 2 sub-Neptunes that are orbiting a bright nearby sun-like star. So what we did in this case was to download the triangle light curves and perform the pre-processing, as I described it before. Here you see the light curves, so the trended light curves. The gray dots are the data. And then the second step is trying to search for the event-like feature. In our case, we decided to use the TLS package, transit least squares package, which performs a brute force fitting of transit templates on a grid of parameters. And we were able to identify, you can see in orange, one planet with a period of around 5 days, and in green, another planet with a period of about 10 days. And there is also one single event here for which we weren't able to determine the period. And this is the zoom in of these transits. So you can see that actually by looking at the data, you don't have a good visual feeling of the transit. By binding the data, you have a much better visualization. Once we found the transit, then we have to exclude false positive scenario, which basically include instrumental artifacts, which can be excluded by if there is nothing weird in the data, and if there is nothing in the TESS manual that reports any problem with the satellite at the time. So this is the easiest scenario to clean. And then the astrophysical false positive. The star, you probably mistake the signal as star in a binary or multiple system, or you can have contamination. That's because TESS has a large field of view, as we said before, which means that the spatial resolution is low. The pixel scale is about 21 arcsecond pixel. So you can have contamination from foreground and background unresolved sources, but also from nearby eclipsing system. So you have to check for all these cases. One way to do that, this is how we did it in this paper, we used the DAVE pipeline, which is software that allows you to do some typical operation on the full frame images at the light curves. Like for the full frame images, you can try to see if there are any offset in the centroid of the images to be sure that there are no other sources in the TESS images. And for the light curve, you can look different way of visualize the events, looking at the second order events or odd even differences, the shapes of the eclipses and so on. But what I want to point out is that the software here will give you the feature extracted or some comments or red flags, but then at the end, the disposition is completely subjective. So you have to decide if the planet is vetted or not. That's why looking at Dave output is such a good project for citizen science. And that's exactly what one of our collaborators has been leading within the Planet Patrol project. So Luca Cacciaporti just published the first catalog from this project called 999. And because vetting is, and in order to avoid this highly this problem of subjectivity, that's why machine learning is particularly good, because then it will give you the capability of reproduce results. Just to complete the discussion of the human interaction-based pipeline, as I mentioned before, you can also use supplementary data, and you can do that by looking, for instance, at bright sources in Gaia surrounding your star, or you can use high-resolution images from ground-based observatory, and then you can search for close stars at close separation within, for instance, in this case, within a 5 magnitude range from the star. And finally, if you want to have a quantitative measurement of the false positive probability of the inference of your final disposition, you can use statistical tools that are available in the literature, like Triceratops, Vespa, and so on. So as you can see, this is a very time-consuming process, and it's highly based on human interaction. That's why what we really want, so ideally what we would like to build at the end, is a completely automated end-to-end pipeline in which we will feed the light curves and get to this position. So that's our final goal. So the first part of the pipeline will still be about performing data assimilation. So you want all the input data looks similar to each other. So this will include cleaning, determining, and binning, and then you want to find your events, and this can be done by using TLS or any other similar software that will just do brute force fitting of the transit shape in the light curve. So this part actually is easy to automatize, because each light curve is analyzed independently from all the others. So this can be, it's a straightforward parallelization. And indeed, we developed GPU parallel algorithms that works on this first part for the pre-processing. And we already published this result. And then we also produced a code that performs apply the TLS fitting in parallel for thousands of light curves simultaneously, and this was run on the Sineca facilities. We still have some computational time to do that, and it will take only 1 day to run for 10,000 objects and more. And this is a project led by one of our collaborators, Pasquale De Luca. Okay, so this part is easy, let's say, and then you want to do the vetting, and this is where you need machine learning. So you need an algorithm that will look all the folded light curve and get a disposition. So in order to do that, we decided to build on what was the best algorithm doing exactly that in the literature when we started, and that was called AstroNet. AstroNet is a convolutional neural network that was published by Charles and Van der Burg in 2018, working on Kepler data, and then the TESS version was published 1 year later by Liang Yu. So we also use a convolutional neural network, and we also use a similar representation of the input data. So we take the light curves and then we do a local view and a global view. So the global view will give you an idea of the entire light curves, and the local view is a zoom in of the transit. And for instance, these are two examples of false positive, and this is an example of true positive. So the net architecture is a convolutional block, and then only one fully connected layer that will provide the final classification. So when you try to build a convolutional neural network for with supervised learning for classification, what are the main challenges that you have to face? Well, in general, if you want to use deep learning, this means that you have a neural network with billions of connections. In some cases, they are called parameters or weights. You can choose your favorite terminology, but anyway, there are basically billions of connections that needs to learn from the data. So you should have a training set that include at least twice as much as data. Of course, this is always impossible in astronomy. So in our case, we only have something like 200 planet confirmed in the TESS database when we started it. So the number is still there. I mean, I'm talking about confirmed planet candidates. So let's say accurate leveled data. So in order to deal with this problem, we decided to use transfer. Well, there are different ways to deal with this. We decided to use transfer learning because we wanted to leverage from Kepler results. So we use a training set that has the DR14 from the Kepler light curves from Kepler, so 15,000 light curves. And then we use the 15,000 light curves that were provided by Liang Yu for the training of AstroNet. Then another problem that you usually face for astronomy is that the class of objects in which you are interested it's usually a low occurrence rate with respect to all the possible false positive. So let's say if we assume that planet candidate is 0.1% of the total data sample, then if your net predicts always negative, it will be 99.9%. But then it will not give you any useful prediction, right? So this is why accuracy is not a good metric to perform to evaluate the performance of neural network. So in order to deal with unbalanced data, and this is also something you can do in a different way, but we choose to use class weighting, which will let's say rebalance the data. So another typical problem is how to do hyperparameter optimization. Hyperparameters are all the parameters that define the learning and the morphology of the net. For instance, the learning rate is a typical hyperparameters. In this case, you have to do some, it's time consuming because you have to find the best trade-off between precision of the net and the generalization. You can have a very good a net that will give very good results on the training set, but then it won't be able to do any generalization, any prediction on a new data set. And that's what is usually called overfitting of the net. So in our case, we decided to use a technique that is called a dropout, in which at some point you randomly throw out a neuron in the net. So basically, the net is forced to learn without the specific feature extracted by that specific neuron. So it's forced to have a more general model. So this is the final architecture of our net. So as I mentioned before, that's the convolutional block, and that's the dense block when we have the fully connected layer that will finally give us the classification. And this is the preliminary result from our net. So when you want to evaluate your performance, then you also need a test set. So another data set that will also have labeled Likert, and that's not included, and that is not included in the training set or the validation set. So completely brand new data sample. In our case, we decided to use the XFOP disposition, so the one that are on the website maintained by the TESS collaboration, which is always, which include all the disposition found for the TESS data, plus 10% of the data sample that we took from the Liang Yu paper. When you evaluate the performance, you can use confusion metrics like the one I show here, in which basically we have the prediction of the net as a function of the ground truth. So here you have basically these are true positive, true negative, false negative, and false positive. Okay, so the color code is the number, the absolute number of planet candidate or non-planet candidate, while the percentage is the relative number of true positive, true negative, and so on. So the first example is by using a net that was only training on the TESS data, and this is a net that was only trained on Kepler data. And this is a comparison with what we think it's our best model, which is a net trained on Kepler and then completely frozen, and then only the final fully connected layer was trained on TESS data. And we get a typical accuracy of 80%, but more importantly, precision and recall, which are defined here, around 87 and 81%, with a final F1 score that it's a metric that combines precision and recall, 0.84. So if we compare this with what was the best available CNN doing exactly the same job, so the vetting of the exoplanets, when we started, then we get a much better performance. So this is the precision recall curve. And you can see that if we look at the recall 0.8, then we get precision of almost 0.9. While in their case, so you have to look at the blue line, which is the vetting part of the CNN. For basically for a recall 0.5, they only get something like 0.7 precision, and it's if you go to recall 0.8, the precision is even lower. So we are. So this brings me to my first conclusion for this part. As I said, our vetting of potential planet candidate is a time-consuming human interactive process, also prone to subjectivity, and that's why the neural network can help us to make everything more automatic and specifically offer reproducibility of the results, which I think is really important. So we, as I mentioned before, we built the best available CNN for doing exactly the same job, the vetting of the TESS data, and included new features, which are the transfer learning, the dropout, reduction of the complexity of the dense block, and we managed to significantly improve performance. And the nice part is that you spent a lot of time training the CNN, but then it only needs a few milliseconds to give you the final classification. And as I mentioned before, this can be included in a completely fully automatic end-to-end pipeline for searching the entire dataset. We started to work on this by using a specific subsample of about 4,000 stars that were included in a catalog by Kaltenegger et al. 2021 that are specifically potential stars that could have Earth-like exoplanets detectable in TESS, because they will be in the regions that I showed before when you have longer baseline for the observation. And the net gives us something like 1,000 new potential planet candidates. So this is, of course, work in progress, but this is one example of the new possible candidate, and it looks like a promising one. Okay, so moving to the next project. This is about finding slow-moving objects in the LSST data. It might seem like we completely changed the subject, but it's not true, because actually comets that are coming from the outer space, like interstellar comets, or comets coming from the Oort cloud, so from the far side of the solar system that are coming in the inner part for the very first time, they encapsulate information about chemical composition of the protoplanetary disk. So basically, they offer the unique opportunity to probe, let's say, in situ, the chemical composition of the protoplanetary disk before planets form. So they are indeed correlated. And that's exactly the reason why this is exactly the goal of the Comet Interceptor mission. So we want to visit a dynamically new comet or an interstellar comet, because we want to visit an object that is relatively less evolved with respect to all the comets we have visited before, trying to understand how the solar system was formed, and in general, planetary system formed. So Comet Interceptor will be launched in 2029, and because of the specific properties of the target, it will probably not be detected before the launch, but will be found only after the launch of the mission. And the target will be very likely identified by LSST. So you probably, I don't know, I think many of you are familiar with the LSST survey, but just to give you a quick overview, this will be the deepest and largest survey of the changing sky over the next 10 years. That's basically because the telescope at the Vera C Rubin Observatory is pretty unique, because it has a large field of view of 9.6 square degrees. You can see here the comparison with the moon. Mounts an impressive array of CCD, but it also has a very good spatial resolution with the 0.2 arcsecond per pixel scale. And it will basically survey the entire southern sky every 3 minutes in multiple bands, down to a magnitude of 25 magnitude in the R band, reaching a photometric accuracy, astrometric accuracy that are unprecedented, basically. So this will be an automated survey, which means that the cadence is decided a priori, is completely automatic. There is no final consensus yet on what will be the final cadence, but this is the general idea for now. Basically, for each pointing in what is called the wide, fast, and deep survey, there will be 2 visits to each position. So each visit is a pair of 50-second back-to-back exposure in a given filter. And then in 30 minutes later, the same position will be surveyed again, will be imaged again. And then the telescope will come back to the same position after 3 nights, and possibly in a different band. So besides all the different backthrough that LSST is expected to do in different science fields, it will also have a huge impact on solar system science. So it's because LSST is expected to at least tenfold the number of objects, solar system objects known for each of the main families, including, of course, comets and interstellar objects. But how detection works? So the LSST will come with an inbuilt pipeline that will do a lot of the preliminary analysis needed. So it will deliver science-ready data. This is amazing. But for the solar system objects, basically what we'll do, we'll use software that will track changing position of the objects from the two subsequent visit pair. So when an object shows significant motion in two subsequent visit pairs, then this motion will be linked together. And then after several observations, they will be all fitted by Keplerian heliocentric orbit. Then the information on the object will be passed to the Minor Planet Center database, and then if it's a new object, will be an alert will be sent. If it's not, then it will be just the new orbital information will just be ingested in the pipeline, so that the pipeline will not trigger again on the same object. That's perfectly great. We want to see very far away objects, like we want to detect long period comets on the incoming inbound orbit, right? This means that these objects will have a very slow motion and they will not be picked by the automated pipeline because they move less than half PSF per night. We want to find them at a separation larger than 200 AU. So we want to do that. And in order to try to do that, we will use a CNN again. The structure of the net is similar, but in this case, it's a three-dimensional neural network because we have to classify video, so time frame of data. We will use small cutouts that are 15 times 15 pixel. And then over the entire observation period of LSST. And then we want a classification that simply tells us if there is an object in that frame or not. So in this case, the challenge of the training is even more complicated because there are no data rights. The survey starts next year. You may know that there are some simulated data called data preview 0. Which basically populates this part of the sky, which is far away from the ecliptic. So, but anyway, there are no moving objects anyway, so it doesn't really matter where it's located, but it's not in a place where you will search for solar system objects anyway. So we have to do everything by scratch. So taking the LSST image and then paint solar system objects in it. This takes time because LSST data can only be accessed through the Rubin Science platform, and downloading all the data from each of the visits is very expensive. For everything that we can do offline, we use a machine at the MIT because this work is in co-supervision with Tansu Dylan that works at the MIT. And this is how the pipeline of producing the dataset looks like. So basically, we pick a random position in the sky. We decide if it will be populated by the moving objects or not. And then we download all the visits from LSST of that specific position in the sky. Ideally, we want to do this for 10 years baseline, but DP0 is only 5 years. But we decided to just start with 1 year of observation because this is already using at least 100 frames for each of the sample. And this is just, I hope this will work. Yay! So these are two examples of a true positive case and a true negative case where the background is real simulated DP0 images. But the zoom is really high because, as I mentioned before, this is 15 times 15 pixels. Okay. Oh. Yeah, and this brings me to my conclusion for this part. As I mentioned before, the complexity of the problem is makes everything a little bit more difficult. We are still working on assembling the training and validation test set. One sample takes 1 hour to be completely downloaded from the Rubin Science platform, and we want to have at least 1,000 samples that will include false positive based on solar system bodies and variable stars. Here you can see an example of variable stars in DP0, but this is a much larger cutout actually. And for now, using the small subsample that we assembled so far, we get 70% accuracy, but many of the cases in which we have misclassification is because the object is going out from in and out from the frame. So that's something we have to fix. And that's it for the second project. Then that's my final take-home messages. Basically, machine learning approaches are a great asset to face the growing complexity and volume of astronomical data. In particular, CNN are particularly efficient for supervised classification and can be applied to a variety of problems. Usually you need to train simultaneously a large number of models, which requires computational resources time, but once the net is trained, then it's super quick in giving the final disposition. And the most difficult part really is building a rich simulated data set that is also representative of the ground truth. For this work, we are really leveraging on the computer science expertise in our department. And in case you would like to collaborate on machine learning based algorithms for your astronomical problem, please reach out.